Okay, good old classic moment of inertia question for the uniform disk radius or about an axis through its center and perpendicular to the plane. So there's our disk, there's the center, and we imagine that the disk is comprised of these annuluses, annuli, whatever the plural is, and that's located at x from the center, and its thickness is dx thick. So the moment of inertia is the integration of r squared dm, and the radius squared is x squared dm. So we'll have to, the x is representing the radius. We'll have to figure out what dm is. So if we look at that sliver, what we could say is the density of this disk in two dimensions, so to speak, is its total mass divided by its total area, which is pi r squared. Not to be confused with that or. So I personally like to use a capital R here, but I want to keep it matched up with the question. Pi r squared. Now, that sliver, so mass equals density times pi r squared. Now that's for the whole disk. Just for the portion of the disk, its infinitesimally small mass, well, what would that equal? Well, what we can do is we can differentiate this dm dr. So that would be 2 rho pi r. So you get dm is 2 rho pi r dr. Yeah. So, well, actually, in this case here, the radius is x. So that means dm equals 2 rho pi x dx. So I can sub that in, that's integrate, and that x is going from 0 to r. X squared, 2 rho pi x dx. That's equal to 2 rho pi integrate x cubed, 0 to r dx. So that's equal to 2 rho pi x 4 over 4, 0 to r. That's equal to 2 rho pi or 4 over 4. So we can clean this up a little bit, because remember that rho pi r squared is equal to m. So rho pi r squared is equal to m, and 2 divided by 4. So therefore we can arrive at the result that the inertia would be a half rho pi r squared makes the m, and then we're left with r squared. And that's great because that's what we needed to get. So that's a perfectly standard proof.